Alright, good morning. So here we are for yet another lovely day or another lovely lesson, same day, lovely lesson, different lovely lesson, of CENG 336, Mechanics and Materials. And this is going to be lesson number 37, which will be the final one on deflection. So after this we'll have two more videos, both covering buckling, which I think I'm going to cover both of them tomorrow, and just wrap things up tomorrow, and then have a free day on Thursday, and then we'll have the final exam on Friday. Now, for this, I want to use, for this lesson, this is covering, in the Hibbler text, 12.2 and 12.5, and we are going to learn how to use deflection tables. And also the principle, so we're going to learn, the objectives for today are to first, to use deflection tables to calculate deflection and slope at a point, and finally discuss the superposition of loads. So what do I mean by a deflection table? Well, I have a deflection, I just so happened to have a beam deflection formula table here. So notice what I have here. I have a series of systems, or series of situations. I have a series of situations and of beams with various support conditions and loading conditions, or various support conditions and loads applied to them. So for example, what I have here is, I have a beam, a cantilevered beam with a point load somewhere along it. In this case, I have a cantilevered beam with a constant distributed load along it. Here I have a cantilevered beam with a point moment on the end of it, and these are simply supported beams here and here, one with a point load somewhere along it and one with a distributed load all the way along it, and this would actually be a fixed beam, a beam that is fixed on both ends. And notice what they have given us. They have deflections as functions of x for each of these. And the great thing about beams is you can use the principle of superposition of loads. So in other words, if I have as long as I have the same length, as long as I have the same material throughout, things like that, if say I have a beam, a cantilevered beam that has both a distributed load and a point load along it. If I want to find the deflection equation for that beam, all I have to do is simply add up the equations for this one and this one. You can literally just linearly add them up. This is based on the principle of linear superpositions of loads. You can literally just add them together. So, but let's look through this here. So, these are very useful because they do save us quite a bit of time. Often, especially when you're doing practical engineering, practical design engineering, you don't want to have to go and derive the equations from scratch for every single case that you're working on. It can be quite onerous to go and do all that calculus for every single case. So often it is more useful to simply look to a table. If a problem has already been solved and you don't need to develop the integral from scratch, just use one that has already been developed. But anyway, we do need to teach you how to develop them, because sometimes you will have things that aren't in a table and can't just be found as the summation of cases in tables. But anyway, so let us look here. So let us recall a few things that we'll need to use here. Let me make sure of something really quickly. Very good. Okay. So let us recall here. Recall. Recall that we have two equations that we need to use that are sort of the basis of all this. Theta of x is equal to the integral of m of x as a function of x, or m as a function of x, over ei dx, and also our deflection equation. Deflection, or y as a function of x, is equal to the integral of the slope. Slope as a function of x, or theta as a function of x, dx. And also for our sign convention for rotations, this is just basic mathematics. We have x and y, and then our theta here. So that's what's relating all of these. We have x, which is going to be along the beam y, which is going to be a vertical deflection up and down, or up or down, and theta is going to be an angle of rotation. Okay, so let us say I have something here. So I'm actually going to have a couple examples today. So first let's do example 1. Makes sense. Example A1. So let us find the, let us say we have a simply supported distributed load beam, or simply supported beam with a distributed load across, a constant distributed load. In other words, really what I want to do here is I want to develop this and see if it matches up with the table. Okay? So let's sort of prove that the table works. So I'm going to have a beam here. It is going to have length L. It's going to have length L. And it's going to have a distributed load W across the top of it. It's going to have a distributed load W across the top of it. W here. And then the reactions here are going to be, since I can't talk, since this is symmetric, this is going to be WL over 2 and WL over 2. And I wish to determine the equation y as a function of x. And I will be throwing that that table PDF on Blackboard after this class. So, solution. Let's just work through it. Well, let's just first get we only need one cut. There are no discontinuities except at the ends of the beam, so we can get away with just using one zone of integration. So I'll look at the shear and the moment first. So let's look at the shear and the moment. All right. So capital V as a function of x is going to be equal to the integral of negative W of x dx, which is equal to, well, in this case, in this case, W as a function of x is simply our constant W. Negative integral of W dx equals negative Wx plus C1. We have a constant integration, we need a boundary condition. So I'm going to go through this a little bit quickly, but it's okay. Boundary condition, V at x equals 0 is going to be WL over 2, and this will lead us inexorably to, we can simply find that C1 is equal to WL over 2. So that will be our shear function. So then for moment, so we know how to do this before. M as a function of x is equal to the integral of V of x dx is equal, dx, not d lambda, is equal to the integral of WL over 2 minus Wx dx is equal to WL over 2x minus Wx squared over 2 plus C2 here. And boundary condition, our boundary condition, M at x equals 0 is going to be equal to 0. And this leads us to, that's C2, like, that is a terrible arrow. That leads us to that C2 is equal to 0. Okay? So next, let's find the slope. I'll do it over on the new slide. Slope, the slope equation. slope here. Well, we know that we have the relationship theta of x is equal to the integral m of x over ei dx is equal to 1 over ei times the integral of wl over 2x minus wx squared over 2 dx, which is then equal to 1 over ei. I will have to come back for a boundary condition because we'll see that why in a bit. wl x squared over 4 minus wx squared, or sorry, wx to the third over 6 plus c3 here. Now, I have the boundary condition, I have a constant of integration. However, this is a pin and a roller support. I do not have any my pin and roller cannot give me any boundary conditions that are useful for slope. So right now, I cannot solve this using say the method we did in previous class or the previous lesson, where we simply looked at the fixed support and said, oh, the rotation there is 0. We don't have a problem. And the rotation is 0 here. Let's find the constant. Here we're actually going to have to solve both C3 and C4 based off of the deflection. But you'll see what I mean by that shortly. And I'm going to dub this equation 1. Then I can say that y, let me label this as deflection. Yeah, I'll do that. Let me label this as deflection. So deflection, y of x is equal, again, to the integral of theta of x dx, which is equal to 1 over ei times the integral of, just plugging this in, wl x squared over 4 minus w x to the third over 6 plus c3 dx, which is then equal to 1 over ei times, oh, that looks bad, little error there, 1 over ei times wl x to the third over 12 minus wx to the fourth over 24 plus c3x plus c4. And this is equation 2. And this is equation 2. So we need to get some boundary conditions. And those boundary conditions are as follows. I know I have a pin and a roller support. So at both of those locations, I don't know anything about the rotation. However, I do know that the deflection at both ends has to be 0. So I know that y at x equals 0 is equal to 0. If I plug this into 2, plug into 2, I get that C4 is equal to 0. C4 is equal to 0. Another boundary condition I have is that y, the deflection, at x equals L is also equal to 0. Now I want to plug this in, plug into 2 along with C4 is equal to 0. And I'll get the following equation. 0 is equal to 1 over ei times wl times L to the third. I'm plugging in L for x. L to the third over 12 minus WL to the fourth over 12 plus C3 times L. And we get that C3 is equal to negative 1 over 24 WL to the third. And then so I can say W is a function of X. I can get my final deflection equation by plugging in the constants. 1 over EI times WL x to the third over 12 minus WX to the fourth over 24 minus 1 over 24 WL to the third X. Or if I pull out all my constants, I can get that Y as a function of X is equal to W X over 24 EI times negative L to the third plus 2L X squared minus X to the third. And that is something very useful. That is down to deflection. So realize what we've created here. This is all in terms of L and W. So this does not just work for a particular beam. This works for any beam. This works for any beam that has the conditions that we laid out. In other words, it doesn't matter what our loading is, W. It doesn't matter how long the beam is. As long as it's a simply supported beam under uniform loading, this will work. In other words, or if I go back here, well, I shouldn't say in other words, let's just say I want to check this. Looking back, look at this. See here? It's the same formula. They use a delta instead of a y like we're using, but it's the same thing. So we have proven that this table is valid for this equation. We have validated this equation. Take it a little further. Here. Now, let's say I wanted to use this a little bit. So what if we want to find theta at x equals 0? Theta at x equals 0. Well, just plugging this in, I would get theta at x equals 0. So in other words, what if I want to know the rotation at the ends? Is equal to 1 over EI times 0 minus 1 over 24 WL to the third, which is then equal to negative WL to the third over 24 EI. So, and also, what if I wanted, so that's the theta at x equals 0. Or what if I tasked us with finding the deflection at the middle, the maximum deflection? This is what the book, or not the book, the table lists as delta, or sorry, as delta max. So what if I tasked us with find y at L over 2, the middle of the beam? Well, we would find, again, just by plugging in, you would find this, that it is equal to negative 5 WL to the fourth over 384 EI, and this will be downward because it's negative. So again, I will give a few notes on the tables. Table notes, they have a little bit different sign convention. The sign convention, they're using a little bit different, so we do need to be cognizant of this. And they're using this kind of sign convention. This would be positive here, where you have a bending angle like this, theta, positive, x is positive to the right, and y is positive downward. So just how that particular table is constructed, it's like this. And again, this is all like, everything we've done here is like case 5. Okay, there's that. And then finally, I want to work through another example that really demonstrates the superposition principle of loads, the principle of superposition of loads. So let me show you an example here. Or actually, this is just another example of going through the tables, but let me see if I want to work through this or not. Yeah, I think I can. Why not? Just using the tables. So this isn't necessarily demonstrating superposition, it's just an example of how you would directly use the tables. In the first example, I proved an example from the table, or proved a formula from the table, and here I'm going to demonstrate how you would just straight up use the table. So example 2, here. So let us say I have a cantilevered beam, and here I have a 10 kip load here, and I have the following dimensions. Say I have 5 feet and 10 feet. So the whole thing is going to be 15 feet long. 5 feet, 10 feet, and the whole thing is 15 feet long. And I wish to find y at x equals 10 feet and Wimax. So in other words, let me show you what I'm going to use. I am going to use case 1 in the beam table. So I'm going to use this case here. There's an A and a B and an L, and I'm going to use these formulas here. So when you're watching this video, download the PDF on the Blackboard site and try to reference along as we go where these formulas are coming from. Here. So again, this is going to be our, from the table, this is going to be our A, and this is going to be our B. So this is going to be case 1 again. So this is, so let me look at the solution. And we are at x is greater than A. We're at x is greater than A because we're trying to find the deflection at x equals 10 feet. So we're looking at the deflection right here, basically. So we're going to use the case where x is greater than A. You need to use 2 different formulas based on whether you're to the left or to the right of the point load. And again, because this represents a discontinuity, so we need a set of 2 equations. So then, y of x is going to be p(a) squared over 6ei times 3x minus a, or 10 kips times 5 feet squared over 6ei times 3 times 10 feet minus 5 feet. And this is then equal to 1041.7 over EI, which is going to be downward. So we get a positive value, but remember this table is using a different sign convention than the one we've been using. So it's 1041.7 over EI downward. I'm leaving out the EI. I'm just doing this in terms of EI. I think you know how to plug in values at this point. Plug in E and I here. So now find Wimax. Find Wimax, and Wimax is equal to p(a) squared over 6ei times 3l minus a, which is equal to 10 kips times 5 feet squared over 6ei, okay, times 6ei times 3 times 15 feet minus 5 feet. And if you want to develop the equation for the max, all you really have to do is take the derivative, find where the that is equal to 0, or find where the rotation, the theta of x is equal to 0. And so y max is going to be equal to 1,666.7 over EI, which will be downward. So that's the maximum deflection at any point along this beam. Now, let's see. Here. Finally, I wish to discuss the superposition of loads and maybe sort of illustrate exactly what this means. So let's look at the superposition of loads. And I'm going to try to squeeze all this on one slide because it is kind of nice to have it all together. The superposition of loads. The superposition of loads. So say I have a beam with a rather complex loading. A beam like this. Not terribly complex, I should say. Maybe something just like this. Say I have a distributed load and a point load across it. Say a 5 kip per foot load, and then a 10 kip load here. And the reactions here would be 40.83 kips and 44.17. Let me actually put this over here to save some room. 5 kips per foot. And then my dimensions here would be 10 and 5. So 10 feet and 5 feet. Like that. Okay, the principle of superposition states that this will be equal, that this is equivalent. As long as we have the same support conditions, this is equivalent to the summation of two other beams. In other words, this is equivalent to this one plus this one here, where I have two different loads. I'll have different loading conditions on each of these. This one will be my distributed, and the other will be my point load. This is 5 kips per foot. And the reactions on here will each be 37.5. And the distance here, the dimension is just 15. Feet. And this will, and then this the other piece is going to be the point load, the 10 kip point load, which you'll end up with reactions of 3.33 kips, 3.33 kips, and 6.67 kips, like shown, where this is 10 feet and 5 feet. Feet and 5 feet, like so. All right, moving along. So if I look, so what do I mean by equivalent? Well, I mean, let's say I draw the shear and bending moment diagrams for these. Let's draw the shear and bending moment diagrams and see what these look like. First, the shear diagram. Well, I can tell you that the shear diagram for this is going to be based by inspection. We're going to go up to 40.83. Then here we're going to be down at negative 9.17, and we're going to drop down to negative 19. And there's going to be a linear line between these two here, and there'll be another line here, and then this will bop back up to 0. And this is at negative 44.17. This one is going to be a simple case like this, where this is 37.5, and this is negative 37.5. And let me just say that this distance here is 8, let me do it in green to show that it's a distance. The distance to that 0 point is going to be 8.17 feet. 8.17 feet. And then the shear diagram for this one is just going to be, we're going to pop up to 3.33, constant across, drop down, constant across, and back up, where this is 3.33 feet, and this is negative 6.67 feet, kips. No, sorry, oh man, that's not feet, that's kips. 3.33 kips. And this is negative 6.67 kips. Negative 6.67 kips here. So we can see that this, let me put some more plus signs in. Plus this, or this equals this plus this. This shear diagram is simply the summation of these two shear diagrams. Or if I were to look at the moment diagram, it's going to be a bit lopsided, but that's okay. It's going to look something like this. Where this is 0, I'm going to have a maximum in the moment diagram. And this maximum will be 166.7, and it will be parabolic. It should be coming to a slope of 0. Something like that. Then we'll be dropping down again parabolically to that point, and then the slope will still be parabolic, but it'll be a different kind of parabola. Something like that, with this 0 at the end. And this would be 158.3. 158.3. And this is equal to the moment diagram here. For this one is just going to be a simple symmetric parabola with a maximum here with a maximum simple symmetric parabola, if we can manage to draw a simply symmetric parabola. Close enough. Of 140.6, and this is plus. For this one, it's just going to be a simple sort of a pyramidal, or a set of two lines with one with a positive, one with a negative slope, and it'll be like this. With a peak at the middle of 33.3. Or not, sorry, not in the middle, just right actually below the 10 kip load. 33.3. And the summation of these two will give the overall shear and moment diagram there. All right, so we have those two. So let's say I have this beam here, and I have those shear and moment diagrams that I created from say formulas in the table or something, or that I created just from finding them. And let's say I want to use the table to find the deflection at a certain location. So using the same, using this beam here, example 3, using the beam above, above, find displacement or deflection at x equals 10 feet. Okay? So the first thing I'm going to need to do is I am going to need to find the deflection at 2 different points. Notice, not 2 different points, it's 2 different cases. So, in other words, the deflection of this beam is at x equals 10 feet is going to be equal to the deflection in this beam at x equals 10 feet plus the deflection at this this beam at x equals 10 feet. So all I got to do is find the deflection at that point for the 2 different beams and then just simply sum them together. So y at x equals 10 feet is equal to 5 kips per foot, just applying the formula. Oh, that looks too much like an integral sign for my taste. 5 kips per foot times 10 feet over 24 EI times 15 to the third minus 2 times 15 times 10 squared plus 10 to the third is equal to 2864.6 over EI. So that is the deflection for the first case. And then the second case, the second simple beam, 2 y at x equals 10 is going to be equal to, and we're in the case of the x is less than or equal to a, that portion of the formula, is going to be equal to 10 kips times 5 feet. All I'm doing is substituting into the formula, times 6 times 15 feet times EI, and this is then equal to negative 10 to the third plus 15 squared minus 5 squared times 10 feet equals 555.6 over EI. So finally, the y total, the total deflection at x equals 10 feet is going to be, or I should say at x equals 10 feet, is going to be equal to 3,420 over EI, which will be downward. Literally just adding this one, and that will be the total deflection at x equals 10 feet. And that'll do it for today. So if you have any questions, feel free to email me. I'll be putting this table on the on Blackboard for you to review as you go through this lecture and work through homework, etc. Now, again, for bits of business for students watching this semester, there is I will hold the final lectures of the course tomorrow, and then I'll post those tomorrow for overbuckling, and then we'll have a break where you can I plan to give you a day to study for the final exam, which will be on Friday from 6 to 9 p.m. So if you have any questions, feel free to email me. That'll do it for today, and as always, thank you.